Okay, we're going to start the second chapter of the Year 13 core work looking at mappings and functions. There's a few things to look at that are on the sheet that I'm going to send. We've got what is called set notation. So we've got particular sets of numbers. We use this sort of strange looking double barred letter to denote them. You'll see this quite regularly as I do some of the examples in a moment. So the ones you're going to see most are probably the Z and the R. N is your natural numbers, the only ones that exist, 1, 2, 3, 4 and so on. Z is your set of integers. If you want the natural numbers only, you could describe it as being the positive integers, but Z is 0, plus or minus 1, plus or minus 2, plus or minus 3 and so on. Q stands for quotient, which are your fractions, anything that can be written as a fraction, where A and B are integers as long as B is not equal to 0. A can be anything at all, and R is everything in real numbers. It's all this lot, plus things like E, pi, surds, any awkward roots, anything like that. We're going to look at mappings. Mappings is an awkward one, especially the second and the fourth of these, and which one's which. It takes the second and the third, sorry, it takes a bit of getting used to. A mapping is any rule which associates two sets of items. So the four we're looking at, 1 to 1. So it means when we stick something in, we get one value out. So in this case here, if it's a straight line function, whatever I stick in for x, I get one value for y out. A many to one mapping is ones like this, like an x squared function, where I can stick in more than one x value to get the same y value. A one to many is a root function, for example, but where we got plus or minus, where I can stick in one x value and I can get two different, 4 and minus 4, y values here. And a many to many is where it's all over the place, basically. You're not probably going to see much of that at all. So that's what mappings are. Let's have a look at what it says about functions. A functions is when there's only one output. So a function is either 1 to 1, the first one, or many to 1, the second one. Is where we only get one thing no matter what we stick in. The graphs of them, all it means is a 1 to 1 is like a nice straight line graph. A many to 1 is it's a curve type function where if we drew a horizontal line across, it would intersect the curve at more than one place. That's a many to 1. Ways of writing our functions down. We can either write it as y equals the function, which is what you're seeing, or f of x equals the function. These mean the same things. Occasionally see it is written as f is such that x goes to x squared is the same thing. So these are all three different ways of writing what our functions look like. A bit of language that you're going to be asked about is domain and range. Now domain is the set of x values we stick in. You'll see it more in the examples I'll do in a moment. But the domain is the set of x values that we're sticking into our function. And the range is the corresponding set of y values we get out. So let's have a look at a few examples then. We've got a nice diagram on your sheet here. Straight line that goes from this point here to this point here. This point is when x is minus 2, and that point is when y is 21. I should really do y and x. And the function is f of x equals 2x minus 7. This is a finite chunk of this infinite function here. So from this finite chunk that we've got, we want to write the domain and the range. The domain is the set of x values we stick in. So I know it starts at minus 2 and it finishes here. So I basically need to solve 2x minus 7 is equal to 21, 2x is 28, x equals 14. So my domain, I can write, because it's set of x values, is x is between, and x is between minus 2 and 14. Notice, shaded in circle there, so there's an equals there, open circle at the end, so there's no equals at that point there. Okay. For the range, I need to find the y values. I've got the y value at the end, 21. I need to find the y value at this point, so stick in minus 2 into our function, x equals minus 2, y equals minus 4, minus 7, which is minus 11. So my range, and in the middle I can either write y or f of x there, and it starts at minus 11 and goes all the way up to 21. Notice yet again, there's the equals at the bottom point, there's no equals at the top point because it's an open circle. So domain has to be set of x values. The range is either the y or f of x values in the middle there. So be aware of the notation there. If you put x in the middle, even if your values are right, you wouldn't get the mark for it. So let's have a look at the second example then. And we've got a quadratic function, and it's written as f is such that x goes to x squared minus 6x. Notation. This is how we write our set notation. It reads as x is in the set of real numbers. This little funky symbol here is short for the little phrase is in. And x lies between 0 and 10. Includes 0 but doesn't include 10. Now, unlike the one before, I can't just stick 0 in that to get the y value and stick 10 in that to get the y value and think, oh, well, that's my range. What I have to do is think about the sketch of it here, because it's a curve, it's going to go down and up in between 0 and 10. So let's have a look at what it would do. X squared minus 6x is the same as, so it would cross the x-axis of 0 and 6. If I sketched it, it would be doing this, and this, and this. So it's crossing at 6. Oops, I don't know the value yet. It's going to go up to 10 there. But in particular, it's going to go down there, and when x is 3, I've got a lowest value there for the function. So if I just took x is 0 in and got y is 0, and x is 10 in to get 100 minus 60 to get 40, the range of values for x isn't from 0 to 40, because I've got to think about the fact it's gone down from there to there. So I need to consider when x equals 3, what does y equal? It equals 9 minus 18, which is minus 9. So that point there is minus 9, that point there is 40. Look at that, beautiful equal scale. So I can say that the range then is y, or f of x, is between minus 9, because it goes down to that, so I can put equals there, up to but not including, because there was no equals for that point there, up to but not including 40. So that's my range of values, considering this is the domain, this is my equivalent range. From that point down to there, that's the lowest value, and that's the biggest value for y in that stretch there. Okay. Last one, we'll look at a sine curve. Here we go. fx is 4 sine x. So I've done a quick sketch of what it looks like there. So I've got minus pi and pi, so it actually means it's going to go up to 2 pi minus 2 pi. That's my domain for the whole bit here. The range of the function then, well, is the top and the bottom values for the y. And since it's 4 sine x, the range of values then is that y lies between minus 4 and 4. And it's inclusive because I can put that point in, I can put that point in there. Okay, so that's my range of values. Yet again, I could have written fx or y in the middle, like that. And part B asks for a restricted domain so that the thing is one-to-one. At the moment, if I drew a horizontal line across, I've got 1, 2, 3, 4 potential values for x. That gives me the same value for y. How do I make it one-to-one? By restricting the domain, the x values that I'm sticking in. And in particular, if I just looked at the chunk there, that little part of the curve still has the same range as before, minus 4 to 4, but the domain now would make it one-to-one. No matter what x value I choose, I only get one y value here. So I'd say that the restricted domain is x, because it's a domain, is from minus pi over 2 up to and including pi over 2. So that makes it a one-to-one function in that little box there. There's only one x value for every one y value and so on, but it's also got exactly the same range as it had before. It's still going from minus 4 to 4.